Today we'll be talking about the development of novel gaseous injectors for rotating detonation engines, specifically the design of a Schlieren system.
The main goal of our work is to develop a Schlieren system to be used in impulse-type facilities. The biggest challenge that we face in our design is timing the recording of the Schlieren images with the milliseconds of runtime.
To ensure accuracy in our experiments, we first modeled the shock tube as two sections of gas, separated by a membrane which is solid and impenetrable. On the left we have our driver gas, which is a higher pressure, and on the right we have the driven gas, which is a lower pressure. The experiment begins when the membrane is suddenly removed, causing the driver gas to rapidly expand towards the driven region. This causes a shock wave to form at the forefront of the flow, and by relating the pressure and velocities between 2 and 3, we are then able to have the shock tube equation, which relates the ratio of 1 and 2 to the ratio of 3 and 4.
Our shock tube setup consists of a high-pressure driver section, a low-pressure driven section, and the test section shown here. The test section is what provides the optical access into the flow needed for our Schlieren visualization. The entire length of the shock tube is also equipped with high-frequency response pressure transducers, shown by XDR. The rest of the experimental setup is not discussed here for brevity. Here's a picture of our shock tube setup. Here you can see the high-pressure driver and the low-pressure driven section here, and the test section at the end. For our Schlieren system, we use a Z-type setup in which the source optics and the receiving optics are separated into two different sections that reflect off of parabolic mirrors. To perform Schlieren, a point source of light is created with a LED source and a condenser, which is reflected off a parabolic mirror to create a collimated beam, which is then deflected by the gradient of density of the flow passing through the beam. That deflected light is either then cut off by a knife edge at the opposing focal point or let through, which is captured by our high-speed camera. You can see here our source optics table consisting of the high wattage LED, the condenser lens, and an aperture to only let the highest intensity light through, shining towards our first parabolic mirror. And then on the other side of the test section will be the receiving side, which has the second parabolic mirror, the knife edge here at the focal point, and the high-speed camera to capture the images. For our data acquisition, we developed a unified LabVIEW program which allows us to precisely time the Schlieren recording and the pressure data acquisition with the quick impulse of the experiment.
Given the initial driven and driver pressures from our transducers in the shock tube, we are then able to calculate our shock strength ratio shown here, which is fundamental for our normal shockwave relations shown below, giving us our theoretical shockwave velocity.
We analyzed our pressure transducer data that we received from the experiment using MATLAB to obtain the average shockwave velocity between each pressure transducer.
Shown on the right is a video of our shockwave passing through the test section in one of our experiments. This was captured with a high-speed camera set at 200,000 frames per second with a shutter speed of 1.5 microseconds. We were able to capture 26 images of the shockwave, and at the end of the video on the left side you can see the reflected shockwave coming back into the test section. Using our 26 high-speed images, we relate the distance traveled to pixels, and these pixels have a known physical distance between them. So using this known distance and the time between photos, we have our experimental shockwave velocity through Schlieren imaging.
This is the result of our calculated average shockwave velocity. You can see between the two experiments that we have excellent repeatability.
Comparing the experimental results to our ideal shockwave velocity, we see that there is reasonable deviation from ideal due to viscous forces and non-idealities, and we also see that the Schlieren image technique corroborated with our transducer time of flight data with an average percent difference of 1.52%. In conclusion, we developed a Schlieren system to be used in impulse facilities and verified the results with our transducer experimental data. Then we compared both methods to our theoretical results to ensure accuracy and validity of both experiments.
In the future, we plan to use this Schlieren setup to visualize the gas injection into our pulse and rotating detonation engines, and we are currently redesigning a new modular test section to include gas injection into the shock tube flow.